Okay, so today we will proceed to our chapter 10, which is the conditional processing. Okay, so actually, it is actually the tutorial for chapter 10. Okay, so we can only do that tutorial after we learn about this conditional processing. So um, in this in this chapter, we will learn about the loop, and then we will learn about jump, all of the instruction that we don't really understand previously, like JE, JMP. Okay, so we will also learn about conditional structure, and then control flow directive. But before we learn all of this, we need to learn about the Boolean and comparison instruction first. Okay. So can we proceed?
Perfect.
Okay.
Okay. So Kelvin, your computer or your Visual Studio already can run the assembly program, right?
Yeah.
Okay, thank God. If not, I will heard you cursing again. Okay, so we proceed like to this. And then this chapter, I think it is also very useful for you all to do your assignment later, because in here we will learn about how to compare, how to do if else, and then there will be various um, examples on how to do if else lah, using assembly language. Okay, so first of all, in the Boolean and comparison instructions, we will learn about CPU status flag. Okay, so here we will learn about the parity, auxiliary flag, and then control flag, all of that lah. All of the status flags. After that, we will learn about this instruction and then its application, and then the test and comparison instruction. And to learn about this status flag, wait, I will need to record our meeting first. Okay, to learn for this status flag, in these notes, it's only tell this definition of all of this flag. Okay, so this is actually the status flag. The status flag containing zero, carry, sign, overflow, parity, and auxiliary carry flag. Okay, so we cannot really see what does it mean by each of these flag, but as usual, I found this video. It is very useful from Mr. Bharat Acharya, and you guys will need to watch this.
Hello people, this is Bharat Acharya. Thank you so much for watching my videos. Welcome to my video again. Today we are learning flag register of 8086, which also includes all the flags of 8085. If you are learning a bigger processor like a 386 or a Pentium, all these flags are included, plus other flags are added. So this is going to be useful to you in all the processors, whichever Intel family of processors you learn. Now let's start. First of all, what does flag register contain? Flag register contains the status, hear me clearly, status of the current result. Okay, we have done an operation. All operations inside the processor performed by the ALU. Every time the ALU performs any operation, it produces a result which goes into an appropriate register, and it also produces a status which comes into the flag register. What you see behind me is the flag register. It has various flag bits. These bits indicate some status, like they tell you whether your result is positive, negative, whether there was a carry, etc. etc. So that's your whole flag register. Now let's start. Flag register of 8086 is this whole register. As you can see, it's a 16-bit register. Before 8086, x86 M8085. That was a total 8-bit environment. So over there, the flag register was also 8 bits coincidentally. Those 8 bits, out of those 8 bits, as you can see, there are 5 flags. So that's what we're going to do. First, we learn the flags of 885, then move on to the 4 new flags signed by 886. Okay. The first flag, carry flag. Out of these 8 bits, there are 5 flags. 3 bits are don't care bits are meaningless. They could be 0 or 1. They don't matter. So the first useful flag is carry flag. Now the name is enough. Carry flag tells you whether there is a carry. Carry out of the MSB get this claim. Not a carry anywhere in the number. Carry out of the MSB. Let's take an example. The best way to understand flags is by example. So I've loaded the board with examples. I will teach you lots of them. Now, suppose we have a number 1111. You can see this is an 8-bit number. The value of this number is FF. To that, we are adding a number 00000001. So what we essentially doing is FF plus 01. Okay, let's do it in Byte. 1 plus 1 will be 0, carry 1. I hope you know that 1 plus 1 is 2, 2 is 1, 0. So 0, carry 1. Again 0, carry 1, 0, carry 1. As you can see, there are all these carries. Finally, that 1 plus 1 will give you a carry coming outside the number. This is the carry that we are looking for. If there is a carry coming out of the MSB, the carry flag becomes 1. For the last time, whether there is a carry anywhere in the number or not is immaterial. If there is a carry out of the MSB, that's when carry flag becomes 1. I hope you got that. Next flag, parity flag. Parity flag tells you the parity of the result. Parity is calculated by the number of ones. So if your result has even parity, parity flag will be 1. If it has odd parity, parity flag will be 0. So suppose our result is, suppose we've done an operation and our result is 1000 0011. Look at the number. There are 1, 2, 3 ones. 3 ones means it's odd parity. So parity flag will be 0. Instead, suppose our result was this. Now there are 2 ones. 2 ones makes it even parity. Even parity means parity flag will be 1. So on and so forth. So the parity flag tells you whether your result has even parity or odd parity. Next, auxiliary carry. Auxiliary carry is the carry from lower nibble to higher nibble. This is different from your main carry. The main carry is a carry that comes out of the MS. Auxiliary carry is the carry from the lower nibble to the higher nibble. Now, I don't know whether you know this. A nibble is 4 bits. A byte is 8 bits. We are grown-ups, as you are also. When we have food, we have bytes. A small child, when he or she has food, we say they are nibbling food. The word nibble comes from there. It means half of a byte. A byte is of 8 bits, nibble is of 4 bits. So you can understand in this 8-bit number, there are 2 nibbles. This is the lower nibble. This is the higher nibble. This is less significant one, more significant. So lower nibble is higher nibble. So if there is a carry that goes from lower nibble to higher nibble, that is what is called auxiliary carry. So if you notice, not this one, not this one, not this one, this one. This was the carry that went from lower nibble to higher nibble. This will make auxiliary carry flag 1, and this will make the main carry flag 1. I hope you understood the 2 carry flags. Next, there is a flag called 0 flag for phonics, the simplest flag in the world. 0 flag tells you whether your result is 0 or 1. If 0 flag is 1, that means your result is 0. If 0 flag is 0, that means your result is not 0. So suppose you've done 6 minus 4, your answer is 2. 0 flag will be 0, right? 4 minus 6, answer is minus 2. 0 flag will still be 0. 6 minus 6, the result is 0, so the 0 flag becomes 1. So whenever the result is 0, the 0 flag becomes 1. Okay, simple. To be honest, very frankly, these 4 flags are just too simple. Even if you teach to a school child, he or she will understand. The important flags start now. The first flag, sign flag. Okay, pay attention to this. This is very intense and very interesting. Sign flag tells you the sign of the result. Sign of the result as in it tells you whether your result is positive or negative. Suppose you have done an operation. This is your result, an 8-bit number. Now, when you look at an 8-bit number in binary form, looking at its MSB, you can indicate whether the number, you can come to know whether the number is positive or negative. If MSB, listen carefully, if MSB is 1, the number is negative. If MSB is 0, the number is positive. First of all, people say, why have they made such a concept? It's very easy, it's very obvious. If on paper you do 7 minus 5, answer is 2. Happy, plus 2. You do 5 minus 7, answer is minus 2. You're still happy, you write 2 with a dash next to it. Now that dash can be written on paper, it can be shown on the monitor. But inside the processor, how do you store minus 2? You cannot put a dash inside a register. Registers are a set of flip-flops. A flip-flop can be a 0 or a 1. So, the idea used is, you need a binary way of indicating whether your result is positive or negative. So the idea used is the MSB. If the MSB is 1, the number is treated as a negative number. If it's 0, it's treated as a positive number. Sign flag directly copies the MSB of the result. Now, what you will learn after this can get a little intense. If you want an easy way out, if you just want to keep it simple in your head without thinking too much, remember this sentence. Sign flag simply copies the MSB of the result. Whatever is the MSB of the result is the value of the sign flag. Okay? So, if sign flag is 1, what is your conclusion? If you say sign flag is 1 means number is negative, you are wrong. Okay? You are wrong. Sign flag is 1 only tells you that the MSB of the result is 1, hence you conclude that the number is negative. If sign flag is 0, MSB of the result is 0, so your conclusion is that the result is positive. Now you might argue that what you said and what I said is the same thing. No, they are not the same thing. There's a word of difference between what you're thinking and what I'm trying to make you understand. As I said, sign flag blinding of these elements. Now to understand this concept of sign flag, we need to first understand the concept of sign and unsign elements. It's going to take about 5 minutes, maybe 10. But if you give me 10 minutes of solid concentration, I'm telling you, never again will you be scared of negative numbers. There are so many people who get totally lost when there are negative numbers in the picture in binary system. If you don't want to be, just understand what I'm saying right now. Okay. So we have an 8-bit number. An 8-bit number can be treated by us matlab you and me, program, can be treated by us in 2 ways. You can treat it as an unsigned number or you can treat it as a signed number. So first let's understand what is this, what is signed and unsigned. Unsigned numbers are numbers which do not have a sign. That means they are always assumed to be positive. As an example, your roll number in a class or the score of a match, a cricket match, always positive. So you don't attach a plus sign to it. It's a number assumed to be positive. So in such numbers, all 8 bits, listen to every word, all 8 bits give the magnitude. There is no bit wasted in telling the sign. Hence the name unsigned. Everything over here is just giving magnitude. Whether MSB is 0 or 1, immaterial, the number is positive. So the concept that I taught you 5 minutes back, telling that the MSB indicates the sign of a number does not apply to unsigned numbers. Okay, that's why the name unsigned. So what you did, 8 bits giving magnitude. 8 bits can give you 2 raised to 8 combinations. 2 raised to 8 is 256. So you can produce 256 numbers over here. All those 256 numbers will be positive. So they will go from 0 to 255. I hope you understood that. Same thing when you write in X system, XRSL, because we work in XRSL. The range will be 0, 0 to FF. How did I get this range? Please don't try to mug up this range. It's very easy to understand. You had an 8-bit number. The smallest value will be when all those 8 bits are 0. The biggest value will be when all those 8 bits are 1. Yeah, when even this bit is included because it's an unsigned number. In unsigned number, that bit has no meaning. They all magnitude. So 8 zeros to 8 ones. Write it as an hexadecimal number, that is 0, 0 to FF. So that is the range of unsigned numbers. Now, the more interesting ones, signed numbers. Signed numbers are numbers that can be either positive or negative. Since they can be either positive or negative, you need to indicate whether they are positive or negative. How do you do that? Not by a plus or a minus. That doesn't work inside a processor. You use the MSB. MSB indicates the sign of the number. So if MSB is 1, the number is treated as negative. If 0, the number is treated as positive. The remaining 7 bits give the magnitude. So again, if you notice, there are 8 bits. Again, 8 bits will give you 2 raised to 8, that is 256 combinations. But all 256 will not be positive. Neither will they all be negative. Obviously, it will be half. The half of 256 is 128. So you get 128 positive numbers and 128 negative numbers. Another way of understanding it, a simpler way. These are 7 bits. 7 bits can give you 2 raised to 7, 128 combinations. I hope you get that. So you can get 128 combinations with this bit as 0 and 128 combinations with this bit as 1. So you can get 128 positive numbers and 128 negative numbers. I hope you understood that. So So your 128 positive numbers will go from 0 to 127. You can see the effect on the range. If you're using unsigned numbers, you have gone all the way to 255, but then only positive. If you use signed numbers, you go only half that point, up to 127. But you get an exactly equal range on the negative side. 128 positive numbers, 128 negative numbers. Positive starts from 0, so goes to 127. Negative starts from -1, so goes to -128. Please don't tell me you didn't get that. Started from -1, so it will go to -128. Okay? Now, this was again the range in decimal, not in press. Let's understand the same thing in byte, in hexadecimal. Come on. Your positive numbers, they will start from 0, 0. Will go up to 7. I hope you don't intend to remember this. Let's understand so that it's there with you for life. You don't have to mug up these things. Come on, look at it. You have totally an 8-bit number. The smallest value will be when all those 8 bits are 0. Biggest value, I'll go on putting ones on them. Now, when you go on putting ones on them, 1, 2, 3, 4, 5, 6, 7. I cannot make this bit 1. Understand? When they are unsigned numbers, putting a 1 over there didn't matter. When they are signed numbers, if I put a 1 over here, the number will become negative. I'm talking about positive numbers. So this bit will have to be 0, which means the biggest number you can produce is this, which is 7. So your range goes from 0, 0 to 7. I hope you understood this. Okay? Similar kind of range will happen on the negative side. Positive started from 0, negative will start from -1. So it will go up to -7f, but will have one more value because it started from -1, so it will have one more value. The value after 7f is 80. I'm sure you know counting very well. 0, 0, 0, 1, 0, 2, up to 0f. After 0f, you get 1, 0, blah, 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 up to 1f. After 1f, you get 2, 0. Similarly, after 7f, you get 8, 0. So positive numbers go up to 7f, negative numbers go up to -80. This is the range for signed numbers. I don't know whether in college you see this range or not, but if you want to understand sign flag and overflow flag, you need to know this range. This range is the whole concept on which those flags are created. So, if you are dealing with a sign number, see, understand, if you talk about sign flag, that means you are in sign system. If you're dealing with a sign number, a positive number should not be more than 7f, a negative number should not be more than -80 or less than -80. And in unsigned system, of course, you can go to 12. Now, suppose I've done an operation, and this is my result. This number can have two entirely different meanings, depending upon whether it's unsigned system or signed system. Please try to answer. Come on. If it's an unsigned, this is 8, this is 3, the value of the number is 83. I hope you understood this, that 1 makes no difference in unsigned system, they all magnitude. Whereas, if it's a signed number, the 1 clearly indicates that the number is negative, and the value is not on face value. This is like basics of negative numbers. Negative numbers are always stored in 2's complement system. Why? The big reason behind it, current short, 2's complement does not produce -0. Any other system you use to store +0, positive and negative numbers will give you a +0 and a -0. 2's complement gives you a unique 0. That's a big logic behind it. I'm not going to do that right now because that's not part of this concept. But still, just to give you in a nutshell. So whenever you see a 1 on the MSB, understand if it's a negative number, it's being stored in its 2's complement form. So when you take its 2's complement, you get 1, 0, 1, 1, 1, 1, 1, 0. This is 7, this is 3. That means this number is -7. In signed system, this number is -70. In unsigned system, the number is 83. The point I'm trying to make over here is, if MSB is 1, sign flag will be 1. If sign flag is 1, that means that doesn't always your number is negative. You have to know whether you're working in signed or unsigned system. If you're working in unsigned system, your number is very much positive. If you're working in signed system, your number is negative. I hope you understood that. Now, suppose we are working in signed system. Okay, signed system. Listen to me carefully. You've done an arithmetic operation. You want to know whether your result is positive or negative. You check the sign flag. Sign flag gives you the value of the MSB. If sign flag is 1, MSB is 1, so your conclusion will be number is negative. I hope you get that. That is not always correct. Here's the trick. Sign flag doesn't always give you the correct sign. Sometimes it gives you the opposite, the wrong sign. When there is an overflow. So this is what you have to understand. The continuation of sign flag logic comes with the overflow flag. Overflow flag indicates whether there is an overflow. If there is an overflow flag is 1. What does that mean? It means you have gone out of range for a sign number. I repeat, you've gone out of range for a sign number. That means a positive number has become more than 7 or a negative number has become less than -8. So what happens because of that? Look, the moment, you've done a lot of hard work. Just give me 2 more minutes and this concept is done. You'll get the whole gist of it. Just 2 more minutes. The moment a positive number becomes one more value more than this is 7f, we are right on the edge. Suppose you add 1 to this. Come on, 1 plus 1 is 0, 0, 0, 0, 0, 0, 0, and the carry comes down over 1. So what you will get is this number. Now this is 80. When you look at it for the first time, there's nothing wrong with it. 80 is fine. When you think of the sign flag, you understand what this whole message is. At this point, sign flag will be 1. If you paid attention to everything I'm talking, sign flag simply copies the MSB. MSB is 1, so sign flag will be 1. If sign flag is 1, you will think that the number is negative. The number is not negative. You added 2 positive numbers. How can the number be negative? What has happened is you gone out of range. Such an event is called an overflow. At this point, overflow flag will become 1, telling you that the sign flag is wrong. I hope you understood this. When a positive number goes out of range on this side, the negative number goes out of range on this side, such an event is called an overflow. At that time, overflow flag becomes 1, telling you your sign flag is wrong. So, moral of the story, putting it all in a conclusion, never directly check the sign flag. Okay, get this clear. If you want to know the sign, before you look at the sign flag, first check the overflow flag. That's how you come to know whether your sign flag is right or wrong. If overflow flag is 0, there is no overflow. Everyone's happy. Whatever the sign flag tells you is the actual sign. If overflow flag is 1, you have overflown the range. At that point, sign flag will give you the wrong sign. Wrong sign as if it's telling you positive, the number is actually negative and vice versa. Okay, let's take examples. Now, the hard work is over. Let's take examples and you'll understand it. I've got a simple one, then a little tough one, then a more crazy one. For example, one by one. We do it interactive. I thought just finish the example. I'll just written numbers, you're going to solve it together. The first example. Suppose we are doing 42 plus 23. Come on, 42 plus 23. The answer should be 5, 6, 65. Simple. 42 is 0, 1, 0, 0, that's 4. 2 is 0, 0, 1, 0, 42. 23 is 0, 0, 1, 0, that's 2. 0, 0, 1, 1, that's 3. 42 plus 23. Answer, let's see. 0 plus 1. 1. 1 plus 1. 0, carry 1. This is 1. This is 0. 0, 1, 1, 0. This is 6. This is 5. Your result is 65. Everyone's happy. Now, let's look at all the flags. Overflow, sign, 0, auxiliary, parity, carry. I hope you can see it clearly. I hope so. The first flag, carry flag. Tell me, what do you think? Carry flag should be 0 or 1? Come on, what do you think? According to me, carry flag should be 0. Why? Carry flag becomes 1 when there is a carry coming out of the MSB. Exactly. There is no carry coming out of the MSB. So at this point, carry flag will be 0. Did you understand that? The next one, parity flag. Super simple. 1, 2, 3, 4. There are 4 ones. 4 ones means even parity. Even parity means parity flag will be 1. Next one, auxiliary carry. It's a carry that goes from lower level to higher level. As you can see, there was no carry going from lower level to higher level. So auxiliary carry flag will be 0. 0 flag. 0 flag tells you whether your result is 0 or not. 0 flag is 1 when the result is 0. The result is not 0. So 0 flag will be 0. Sign flag. Please get this right. Come on, please get this right. What did I say? 10 times I repeat. Sign flag is 1 when MSB is 1. Sign flag is 0 when MSB is 0. Sign flag simply copies the MSB. MSB is 0, so sign flag will be 0. Telling you that the result is positive. You have added 2 positive numbers, the result is genuinely positive, which means there is no overflow. How do you understand? Your result is 65. Overflow happens when you cross this number, when you cross the number 7. You have not crossed that. So there is no overflow, simply telling you that your sign flag is correct. I hope you understood this. This was a very easy example. I'm going to raise it a little bit. I'm sure you give you answer. I have number 37 and 29. Let's add them. Add them. If you're thinking it's hexadecimal numbers. I hope you know hexadecimal addition. Best suggestion, just take a calculator and do it. We are not learning how to do hexadecimal addition. Still, if you want to know, it's too simple. 9 plus 7. Do it one by one on your fingertips. 9 plus 1 is A, B, C, D, E, F. 1, 0. After F, you get 1, 0. Which means this will be 0. This will be 1. 3 plus 1 is 4 plus 4 is 6. Your answer is 60, not 66. Okay, let's do it by 1 plus 1. 0, carry 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 1. 1 plus 1 plus 1 is 3. That is 1, carry 1. And it's 1 and 0. So what you get is 6, 0, 60. I hope you got that. Now, flags. Come on. I hope you answered before I spell it out. If you want to use the time to think, carry flag. There was no carry coming out of the MSB. Carry flag will be 0. Parity flag. There are 2 ones, even parity. So parity flag will be 1. Auxiliary carry. There is clearly a carry going from lower nibble to higher nibble. Can you see that? This one. This makes auxiliary carry flag 1. 0 flag. The result is not 0, 0 flag will be 0. Sign flag blindly simply copies the MSB. MSB is 0, so sign flag will be 0, telling you that the number is positive. The number is positive. You add it to positive numbers. It's not an overflow. Your result is 60. 60 is well within the range of sign numbers. So overflow flag is 0, telling you that your sign flag is correct. I hope you got this. Take any 2 numbers, try to solve them. If you don't get them, just put a comment on the video. I'll solve it and give it to you. But that will never happen. If you understood the concept, you paid attention to the whole video, you should be able to get it. Now, both these examples were examples of not an overflow. Now we do one last example of an overflow. Just so that you know what goes wrong if there's an overflow. 42 plus 43. If you add them, you will get the answer as 85. Before I go ahead, what do you think? Is this an overflow? Has to be. You have to stop at 7. Any number beyond 7f will give you an overflow. So what happens? 0 plus 1. 1 plus 1. 0. Carry 1. 1. 0. 0. 0. 0. Carry 1. And this is 1. This is 8. This is 5. Your number is 85. Nothing wrong with the magnitude. I never said the magnitude will be wrong. I said the sign flag will be wrong. Come on, let's hit the main point. At this point, sign flag is 1 because MSB is 1. Anyone who doesn't know all this logic thinks sign flag is 1, so number is negative. Come on, tell yourself, how can the number be negative? You added 2 positive numbers. This is what examiners do in oral exams, by or even in interesting technical exams. This very question. You added 2 positive numbers, you bound to get a positive answer, then why is sign flag giving you a wrong result? You got to answer at this time, this event is an overflow. You have gone out of range. If you're talking about sign flag, you better should realize you are in sign system. In sign system, a value cannot be more than 7. This is a valid value if you're in unsigned system. And if you're in unsigned system, sign flag does not even make sense to you at that time. So if you talk about sign flag, you should be in the range of sign numbers. You've gone out of the range. So at this point, there is an overflow telling you that the sign flag is wrong. I hope you got that. Remaining flags are too simple. Don't shoot. Carry flag, there's no carry out of MSB. 0. Parity flag 1, 2, 3. Or parity 0. Auxiliary, if there is no auxiliary carry. 0, 0 flag, the result is not 0, so it will be 0. Okay? I hope you understood all the flags. Now, the flags we saw right now.
Okay, guys. Enough with the sign status flag. Okay, it took about 25 minutes our time, but it's okay. I think because that video is very helpful for us to understand how we get all of this status flag. Okay, so can you guys understand the video just now?
A bit.
A bit
A
lah
little
kan?
bit,
Pardon, Vera?
a little bit.
Okay, Kelvin?
Oh yeah.
Okay, so as that guy said that 0 carry and parity and auxiliary carry. So these 4 status flag is easy to understand lah kan. But the only complicated, a little bit complicated just now is the sign. Sign also simple lah, because it only copy the MSB value. Whatever MSB value it will directly copy the MSB value. And then the overflow, if it is over the range of either it is signed or unsigned value. Okay, I will repeat again lah. Okay, zero flag is when the result of your operand is equal to 0. So zero flag equal to 1 if the result is all 0, and then it will be 1 if the result is other than 0. Okay, whatever number, as long as it is other than 0, then your zero flag will be 1. Will be 0. Okay, the zero flag only will become 1 when the result is equal to 0, meaning all the number is 0. Okay, so for the carry flag is the flag that is when you have a carry that is outside. It is outside the MSB lah. You remember the MSB is most significant bit, which is at the leftmost bit in your binary number lah. Okay, sign flag is the flag that is it will copy directly the value of the MSB. So it doesn't matter either your number is unsigned number or signed number, it will copy directly the MSB value. And then in signed number, if you guys remember just now, if the MSB is equal to 1, that can indicate that your number is a negative, but that is not always the case. Okay, that is not always the case because there are conditions. Because to make sure that the number is, let's say we are talking about signed number. Okay, so the number 1, if your sign flag equal to 1 and then your number is signed number, it doesn't really confirm that the signed number is actually negative. Okay, so because there are condition. Okay, so if the signed number flag is equal to 1, in unsigned number, although it is 1, your number is actually always positive. Remember, unsigned number always positive, even though your signed flag equal to 1. But in signed number, there are some condition. Okay, so in signed number, if your signed flag equal to 1, it doesn't really confirm that the number is actually negative, because we need to see the overflow flag number. Okay, so the conclusion from the very long explanation that Mr. Bharat Acharya told us just now is, in sign number, I think I will let's see. In sign number, if your sign flag equal to 1, it is not necessary. Sign flag equal to 1, and your overflow flag equal to 1, then that number is equal to negative number. negative number. But if your sign flag equal to 1, and your overflow flag is equal to 0, sorry, this is positive number. So it means it is negative number. Okay, so this is also n. There's n condition there. Okay, so in sign number, if your sign flag is 1, it doesn't necessarily that number is actually negative, because if we see the overflow, if the overflow value is 1, then the number that is showed in the binary number is positive. But if your sign flag equal to 1 and then the overflow is 0, then the number is memang negative lah. Okay, so I will save this. Okay, so that is the conclusion from the long explanation just now lah. And then the overflow flag is set equal to 1 when the number in the result operand over the range of that particular number. For example, if it is signed number, if it is unsigned number, the range is only 0 until 255 decimal. And if the binary number or if the result is over than 255, meaning for example if 256, then the overflow flag will be set equal to 1. Okay, so the same with the sign number, which is the range is from negative 1 to 8 until positive 1 to 7. If the result showing the number that negative 1 to 9, which is over the range, meaning the overflow flag will be set. Okay? Understand that part?
Okay.
Okay, so if you don't understand, then just ask lah. About the parity and auxiliary, who don't understand?
Me.
You. Parity is when there are a number. When there are a number, you only focus on bit 1. I mean, if the bit is 1, 1, 0, 0, then 1, 1. Okay, so this is 8-bit number. I don't know if you guys can see. Yes. Okay, so for the parity flag, you see the number 1. If this the frequency of the number 1, this is 1, 2, 3. Is it odd or even?
Odd.
Odd, right? So the parity flag will be the parity flag will be set to 1 if the frequency of number 1 here is even. Okay, so this one, meaning for this number, the parity flag there is equal to 0 because the frequency of number 1 here is odd. Okay, so if it is like this, okay, so the frequency of number 1 here, 1, 2, 3, 4. 4 is odd or even?
Even.
Okay, so if it is even, then the parity flag will be 1. Okay, only focus on that lah. Okay, that is the parity. For auxiliary carry, who don't understand?
Me again.
Okay, so let's say this one. If you add this to number, or if we have we add this number lah, okay. Okay, so for this one is 0, 0, so this one is 0. And then this 0 plus 0, the result will be 0. 0 and 1, the result will be 0 also. 1, sorry. But 1 plus 1 will be 10, right? 0, and then you need to carry 1 here. Okay, so if we divide this into nibble size. Nibble size meaning 4 size of 4 bit. Okay, so if there are a carry from the bit number 0, 1, 2, 3. Okay, from the bit number 3, you because when you add this, there will be a carry to the bit number 4, right? Kan Vera, ada carry kan sini di atas dia?
Yeah.
Okay, so if you add the bit at position 3, and then it will produce a carry to bit number 4, or to the bit in the position of 4 here, then that means your auxiliary carry will be 1. Okay? If okay kan Vera?
Okay.
Okay, so if like this, 0 plus 0, there will be no carry kan to bit number 4. Okay, so that means your auxiliary flag will be 0. Okay, the auxiliary. Just remember the auxiliary carry is a carry out from bit 3 to bit number 4. Okay, so this is bit number 3, this is bit number 4, because remember it start with bit 0, 0, 1, 2, 3. So this is bit number 3, and then this is bit number 4. Whenever you add bit number 3 and then it cause a carry to bring over to the bit number 4, meaning your auxiliary carry will be 1. Okay.
Okay.
Okay, so we proceed. Okay, so then we have finished the CPU status flag. There are 6 status flag that we have just learned just now. I hope you can remember all of that status flag. And then now we learn about the AND, OR, XOR, and NOT instruction lah. Okay, but in this in this lecture, you remember and I mean all of this instruction, and meaning if you add two number, it doesn't matter here. And meaning only when 0 will be 1. I think I will show you guys the video of this lah. Okay. After that, baru we learn the application of it. Okay. So Sam, this is a shorter video lah. It only takes 10 minutes.
Hello people, I'm Ascii. Welcome to my video. Thanks for watching all these videos. You've been really encouraging me a lot. Your comments are all welcome. Thank you so much. Today's video, I'm going to teach you logic instructions of 86. They are so badly overlooked. So many people focus on the arithmetic instructions, the complex arithmetic instructions, completely ignore these instructions because they're too simple. But hello, there are situations which if you get into, only a logic instruction can get you out. And even in exams, many times to surprise students, they ask these instructions, their applications, because many people ignore them. They just treat them very lightly. They're not supposed to be. They're very simple, but they have their own good use. Okay. So logic instructions explore the logic gates. You know the three basic gates: AND gate, OR gate, and XOR gate. So instructions are very simple. AND, BL, CL. We do BL, AND it with CL, and we store the result in BL. BL is an 8-bit register. CL is an 8-bit register. When you AND them bit by bit, the result will also be an 8-bit number. That 8-bit number will be stored in BL. Of course, I'm going to teach you the application. First, I'll just run through the instructions. Or BL, CL will do BL or CL. XOR will do BL, XOR CL. Not BL will simply do BL part. So one's complement. So it's like a NOT gate. And test BL, CL will do the same thing as AND, but AND will store the result in BL. Test will not store the result, will only affect the flags. And it will only affect the flags. Now, what's the use of these instructions? First, let's come to this one, not instruction. You got AND gate, you got OR gate, you got XOR gate. Suppose somebody just asks you, what if I want to do a NAND? What do I do? Now, if you know your gates properly, what is a NAND? An AND gate followed by a NOT gate. So first perform an AND, follow it up with a NOT, that is as good as a NAND. OR followed by a NOT is a NOT. XOR followed by a NOT is an XNOT. So the job of NOT gate is to produce those three derived gates, the NAND gate, NOT gate, and the XNOT gate. Tell me, did you understand that? Now, what's the use of these operations? AND, OR, and XOR. They are so interesting. You'll be wow once you know it. Just 2-3 minutes. AND 0, 0, 0, 1, 1, 0, 1. Okay. So we'll give you 0, 0, 0, 1. I'm sure everybody knows their gates. Yeah. OR gate 0, 0, 0, 1, 1, 0, 1. We'll give you 0, 1, 1, 1. XOR gate 0, 0, blah, blah, blah. We'll give you 0, 1, 1, 0. So let's use that. Suppose BL register is 0011 0101. It's an 8-bit register, so it has an 8-bit value. This is 3, this is 5, so the number right now is 35. So BL right now has the value 35. Are you with me? Now, suppose somebody tells you, clear the lower level. Clear the lower level means, this is the lower level. It should become 0, but the higher level should remain the same, which means 35 should become 30. So you would say, what's the big deal? Subtract 5. Yeah, my friend, you will subtract 5 if you know that the number is 35. What if the number was 37? Then you have to subtract 7. Problem is, you don't know what the number is. I tell you, this is a number I've got from memory. Now clear out the lower level without affecting the higher level. You don't even know what the number is. How will you know what to subtract? So here, no kind of arithmetic operation is going to help you. What you need to do now is a logic operation. Which one are you going to do? AND, OR, or XOR? Obviously AND, this is next to AND, this is next to OR, this is next to XOR. So this is going to be done by AND. See the beauty of arithmetic. Come on. Many people know these gates but have no idea why these gates are made. Look here. 0 or 1. Anything, if you AND with 0, becomes 0. But anything, if you AND with 1, remains the same. I repeat, anything ANDed with 0 becomes 0. Anything ANDed with 1 remains the same. So that's the idea we're going to use. I will AND these bits with 0. So whatever they are, they'll be wiped out and become 0. But you can't do a 4-bit operation. If you're doing, you have to operate on all 8 bits. So in order to not affect this part, you'll AND these bits with 1. Anything you end with 1 remains the same. Anything you end with 0 becomes 0. This number is F, this number is 0. If you read out the whole thing, that is F0. So if you end BL register with the value F0, you adding BL with F0, the result will come in BL. This will be your BL. 35 will become 30. If you know practicals, if you've been for practicals, type F0 as 0 F0. Every number that begins with an alphabet should have a leading 0. Otherwise, the assembler assumes it to be a variable and will tell you a defined variable and you know you to assemble the program. Anyway, that's apart from this. The point is, that's just for the sake of assembly. What you've done is this is F, this is 0, adding this number with F0 will wipe out the lower nibble but maintain the higher. Tell me, did you understand this? So if you want to clear the lower nibble, you add it with 0. Similar, one more example. BL is 35, again the same number, 35. This time I want you to set the lower nibble. Set the lower nibble means lower nibble should become all ones, but higher nibble should remain the same. Okay? What do you do now? AND or XOR? Yeah, or. Anything you OR with 0 remains the same. But anything you OR with 1 becomes 1. Again, anything OR with 0 remains the same. Anything OR with 1 becomes 1. So, if you want to make the lower nibble 1, all these bits with 1, whatever they will become 1. Then did you understand this? But all these bits with 0, anything OR with 0 remains the same, anything OR with 1 becomes 1. So what is this number? 0F. Or BL with 0FH. The result will come back in BL. Higher level will remain the same, lower level will come all ones. Did you understand? So to clear you use AND, to set you use OR, similarly to complement. This is your lower level. I want you to complement the lower level. 1 should become 0, 0 should become 1, 0, 1. But the higher level should remain the same. Now I don't want to complement the whole number. Please understand, if I want to complement the whole number, I do a NOT operation. A not BL. Will simply do a complement of the whole number. That's the whole case. I don't complement the whole number, only the lower level. So look here. 0 or 1, anything if you XOR with 0 remains the same. But anything if you XOR with 1 gets complemented. See for yourself. 0 is becoming 1, 1 is becoming 0. I repeat. Anything XOR with 0 remains the same. Anything XOR with 1 gets complemented. So, XOR these bits with 1, these bits with 0. This will remain the same, but this will get complemented. The number is 0F. You will do XOR BL, 0FH. The result will come back in BL. Tell me, did you understand this? So, to summarize, when do you use each one of them? They ask this even in oral questions. Why? They ask this in entrance exams. All of this with examples is there in my book. Okay, an 8-bit register. And there are many more examples in the book. I'll give you one more. So this is a very typical question asked in Viva in oral exams. An examiner draws a register, an 8-bit register, and points at any one bit. Okay, so I'm pointing at this bit. He or she, whoever is your examiner, will tell you, make this bit 1. Don't affect anything else, but make this bit 1. How do you do it? You want to make it 1. Come on, my friend, come on, make it 1. What do you do? AND or XOR. You want to make it 1. You will OR this bit with 1, or everything else with 0. The number is 1, 0H. If you OR this register with the value 1, 0H, all other bits will remain the same. You don't even know what they were, but they will remain the same. But this particular bit will end up becoming 1. Tell me, did you understand this? I draw a register and I tell you, make these 2 bits 0. Don't affect anything else, make these 2 bits 0. And these 2 bits with 0, but the remaining bits with 1. I tell you, make these 2 bits complemented without affecting anything else. XOR these 2 bits with 0 and then XOR these 2 bits with 1 and then remaining bits with 0. So the idea is, this is a register, 8-bit register. If you want to make any bit 0 and that bit with 0, remaining bits with 1. If you want to make any bit 1 or that bit with 1, remaining bits with 0. If you want to complement any bit, XOR that bit with 1 and the remaining bits with 0. These things cannot be done by any arithmetic operation. If you get a question like this in your exam, the only thing that can bail you out is the knowledge of logic instructions. It's just not you should know it, because so many people ignore it thinking they are simple. Yeah, they are very simple, but what they do, no arithmetic instruction can. Okay, I hope this video was useful. It was worth your time. Please send me all your suggestions. I appreciate. I try to reply to each one of them as much as possible.
Okay, done. I skipped some part because it is the part where he is promoting his book. Okay, so basically that video just now, it is telling about this instruction. Okay, so that instruction, the summary of it is, okay, so I want to screenshot some of the video here.
It's an 8-bit register, so it has a...
Okay, so in our notes, it didn't tell in detail what is all of this, right? So that's why I show you guys the video just now. And then now we proceed to the application of all of this instruction or this Boolean instruction. Okay, so this is the application of how we can use AND, OR, XOR, and NOT. Okay, so let's say that the question is asking, you need to convert a character in AL to uppercase. Okay, so let's say the character in your AL is A. Okay, so in binary, A is actually this one. Okay, so if you get some questions like this, you just you go to any converter online, and then if you want to know its binary, either it is A, for example, just now is A, right? Okay, so you have this one, this number. Okay, so it says here, convert a character in AL to uppercase. So let's say the character is A. Okay, so its uppercase will have another binary number. It will be represented by another binary number. So if we can see, the small case of A is represented by this, which is the same with this one. And then we want to make it to be a capital letter, kan? Capital letter A. Okay, so we have this number. Okay, so to make the small letter, this one, to this one, we need to make, if you can see here, we need to remove or we need to convert the bit 5 here to become 0. Because if we make the bit 5 equal to 0, then this number will become capital letter. Same like what is shown here. Okay, so because capital letter only containing this number. Okay, so to make the small letter to be its capital letter, for this case is A, we need to make bit 5 to be 0 because currently the bit 5 is equal to 1 in small letter. So how we can make that 0, that 1 here will become 0, and then all of the remaining bit will stay the same. So that's why we use AND instruction. because we want to clear bit 5. So that's why only, because we know that if n only when both, we can see the rules here, and 0, 0 will be 0. 0, 1 will be 0. Meaning, and then 0, 1 and 0 equal to 0. And then only when 1 and 1, and then the number will be 1. Okay, so by following this rule, we search a number that can make this one to become this one. Okay, so because we want to only make the bit 5 is equal to become 0, so that's why we need to end it with this number. Okay, because if we 0, I'm sorry, from the right side first, 1 and 1 equal to 1. Okay, so 0 and 1 equal to 0. Okay, so 0 and 1 equal to 0. Okay, so only when this one at the bit 5, 1 and 0 will become 0. So that's how we can use AND instruction. Okay, so can understand this part?
Oh yeah.
Okay. Okay, so just as the conclusion kan from the Mr. Bharat Acharya notes just now, when we want to clear something, we need to use AND. Okay, when the question is asking instruct about set, means here set, this previous question is clear, right? So if we want to clear something or delete something, we use AND. If we want to set, meaning we want to make that bit equal to 1. Okay, so that is the meaning by to set. To set meaning to make it 1. Okay, for this example, we want to, the question is to convert a binary decimal byte into its equivalent ASCII decimal digit. Okay, so for 6, the binary of 6 is this one, right? Okay, so we want to convert this binary to its ASCII decimal digit. The ASCII decimal digit, we can search here. We can convert it here. For example, 6. 6 in ASCII format is this one. Okay, so 0, 1, 1, 0, and then this one 0, 0, 1, 1, which is equal to this one. Okay, so we want to convert this one to this one, so we need to set, meaning bit number 4 and number 5 to be 1, because bit number 4 and 5 here is equal to 1. But in binary, in binary number it is 0 kan? So to make this number to be this number, we need to make bit 4 and 5 equal to 1. So if we need to set, we need to use OR. Okay, so to make this number or to set this bit 4 and 5 to become this number, then we need to find a number that we can OR it with this number so that it can resulting in this number. Okay, for example, this one, if OR rules is this one lah, we can see lah, whenever there's an 1, the result can be 1. Okay, whatever okay, whenever they are 1, then the result can be 1. Only when both are 0, then the result barulah will be 0. Okay, so we need to find a number. For this one, we need to create it ourselves. Okay, so the same with this one, n. We need to create this number so that we can create the result, because the result is already told, right? In the question, it says here, so that it can become uppercase. So we already know what is the result. So we need to create the number that we can AND or we can OR with the existing or with the first number to become the second number, to become the result. Okay, so for this one, we need to create this number so that we can OR it with the first number. Okay, so for this one, we need to add 1, 1. I mean, everything is 0 except for the number in bit 4 and 5. Because using OR, doesn't matter either the first number is 0 or 1. As long as there is a 1, then it becomes the 1. So that's why we can create, or we can create this number. And then we OR it with the first number, and then we can get this result. Okay.
Okay.
Okay, so that is the application of AND and OR. And then for the test is actually, it is similar with AND operation, but we do not need to make our operand destination here. We don't need to do any operation like this lah, because the test instruction is already predetermined in the register in our computer, that it can produce the same result with n. It's just that it didn't change any register or destinations. It only will modify the 0 flag. Okay, so meaning 0 flag will be affected either 0 or 1 lah if the result is okay. So actually test, it cannot be used by itself. It must be used by some of the other operations like JNZ and JZ. Okay, so these actually are operation of jump, but we will learn it in our next slide lah. Okay, so the highlight here is the test of instruction is the same with AND operation, but the difference is no operands will be modified, but only 0 flag will be affected lah. Okay, so we proceed to the comparison instruction. So in this comparison instruction, it compare the destination operand to the source operand. Okay, the syntax is compare CMP, your destination, and the source. Okay, so this is the syntax or the example of how we can compare. Okay, so first we set the AL equal to 0, and then after that we compare the AL with 5, meaning compare 5 with 5 lah. Okay, so this is the example of how you can code when the destination is equal to the value of the source. Okay, so 0 flag will be set. In this condition, if the destination equal to the value in the source, the zero flag will be set. Meaning, if it is set, meaning it is equal to 1. Okay, if zero flag is set, meaning zero flag equal to 1. And then for the when we want to compare a destination that is smaller than the value in the source, then this is the example. First, we need to set 4 to AL first, and then we compare the AL with 5, meaning the source when destination is smaller, whatever we put in the AL will be the destination lah. Okay, whatever we compare with the AL, meaning the source. Okay, so now source is larger than destination. Okay, so in this condition, this is the carry flag will be set. Okay, so we know that this destination value is smaller than source if the carry flag equal to 1. Okay, so this is the fact or the rule that we need to remember lah. To using comparison instruction, we need to see the zero flag if we want to compare either the value is the same or not. And then if we want to compare either the destination is smaller than source, we need to see the carry flag. After that, if we want to confirm either the destination value is larger than the value in the source, then we need to see the value in zero flag and in the carry flag. If it is both zero, meaning the destination value is larger than the source value. Okay, so this is the rule that we need to remember. Okay, after that, this is still in comparison instruction. So this is the example when we want to compare the sign value. Previously, it is unsigned integer, and now this is the example for signed integer. Okay, so if we want to know either the signed integer in the destination is larger than the source, then we need to see the sign flag. Okay, so if the sign flag equal to the value of the overflow flag, then it means that your destination is larger than your source. Okay. After that, if we want to know that the destination value, either the destination value is smaller than the source value, then we can see, we need to check either the sign flag is not same with the overflow flag. Meaning, if it doesn't, it didn't same, it did. If it don't have the same value, then it is confirmed that the destination value or destination number is smaller than the source. Okay. Okay, with this comparison instruction.
Okay.
If you
Okay.
okay, so if you don't understand, just stop me lah.
Miss, if like
Yes.
both the value is same, or
Pardon? Most of the value is same.
if the destination same with source.
Oh, for the sign integer.
Yeah.
Okay, wait. Yeah. Okay. In this example, there are no example for the same. Okay. So it will be wait. I think first.
same as previous.
Good question.
Is it same as previous?
I am not sure. I think yeah lah, but I think yeah. But let me double confirm with you lah, okay? because I cannot give wrong info kan. I think yes, because it didn't they didn't show it here, right? Okay, so it does usually it will it means it is the same with the unsigned number lah. Okay, meaning zero flag will be set if it is the same. But I will double confirm on you about this. You remind me if I forget about this. But for now, we can assume that it will be the same with the unsigned number lah. If the destination same with the source, meaning the zero flag will be set. Yeah, I think lah. It will be the same. Should be the same lah. Okay. Okay. Now we proceed to the conditional jump. Okay, so here we will learn about JMP lah, JE lah, everything that we don't understand previously, then we will learn here. Okay, so we can jump. We can use jump instruction based on specific flags or the equality, unsigned comparison, and sign comparison. Okay, so we will see that later in our next slide. And then after that, we will learn some of the application of jump instruction lah. Actually, there are a lot. We need to remember lah. Or not only remember, you only can remember all of this instruction if you use it or if you apply it in the code. If you just read all of the definition, of course, you will not really remember that. Okay, so the J condition instruction actually jump instruction lah, but it will jump with some condition. Okay, so a conditional jump instruction branches to a level when specific register or flag condition are met. Okay, so this jump, it will jump to any level that we will specify later only if the condition is met. Okay, for example, the JB or JC, this instruction will jump to a level if the carry flag is set. Okay, so we will see later lah dia punya example. After that, JE and JZ. If I'm not mistaken, the difference between this is JB you use for unsigned number, JC you use for signed number. Okay, so JE will be used for unsigned number, and then JZ will be used for signed number. Okay, so we use this if we want to check the value of zero flag. Okay, so we will jump to a level that we will specify later if the zero flag is set. JS meaning you will jump to a level if a sign flag is set. JNE and JNZ meaning JNE ni is the opposite for the JE, meaning jump if not equal. This one jump if equal to zero flag. This one jump is JZ. JZ is jump if the zero flag is set. JE jump if the value is equal to the zero flag. Okay, so this one is the opposite of this one. This is meaning you need to jump. You will the instruction need to be to jump when the zero flag is not equal with the value that you want to compare. Okay, so this one is jump when the value you want to compare is not the same with the zero flag. Okay, so for JEECXZ, meaning you will jump if the value of in the ECXZ equal to 0. Okay, so there are another example like JCXZ, meaning this one is only used for 32-bit processor because ECX is a 32-bit register kan. For the 16-bit register, you can use JCXZ, meaning you will jump to a level if the value in the CX register will be 0. Okay, so your counter, when you want to jump to any of the when you want to loop or you want to while make sure that the counter, if we are using if you are using 8-bit processor, the counter should be in this range. Okay, this one ECX. Remember, ECX is the register that holding the counter. Okay, so if CX pula, it is used for it is used for 16-bit counter, a 16-bit processor counter. Okay, so for the 16-bit, 16 kah this one? I think this app lah. Okay, this is when you only have this is actually yang 8 bit. Wait, I cannot give you. But I know that 32-bit offset permits jump anywhere in the memory because the counter will be a lot lah. It didn't limit, but for the, I think this is 8-bit register lah, because it only up until 1 to 8 until 1 to 7 byte. Okay, so this is for 8-bit processor. 8-bit processor. Okay, so this is the jump based on specific flag. So you can see here lah, JZ jump if 0, meaning jump if your 0 flag equal to 1 or if your 0 flag is set. J and Z meaning jump if your 0 flag equal to 0. JC jump if your carry flag is set. JNC is the opposite lah. JO if your overflow is set, JNO is the opposite. Okay, JS if your sign flag equal to 1 and JNS is the opposite of it. JP is your parity lah, parity flag. Okay, so you jump if the parity flag is set. Is set meaning the number is 0 or 1. Okay, so if JNP meaning you jump if the parity flag is not set. Okay, so after that, this is the the jump based on equality. Previously is this jump based on specific flag, all of the flag that we have learned previously. And then this one is the jump based on the equality. Okay, so this one JE jump if equal, meaning if your two operand have equal value. Okay, so JNE, if your two operand that you want to compare is not equal or not the same value, it have no, it not it not has the same value lah. JCXZ jump if the CX register equal to 0. So like I said just now lah. So this one is JECX, meaning your 32-bit register counter is equal to 0. This one is the register counter for 16-bit number. After that, so this is jump based on unsigned comparison. Okay, so this one is only for unsigned. Okay, so this one is for sign. Like I said just now, there are some example that we saw previously. Okay, so JA, jump if above value, the left operand is larger than the right operand. JNB is jump if not below or equal. Okay, so same as JA lah, but jump if not below or equal. Okay, so this is actually the same. If we think logically, it is the same lah with this one. Okay, so JAE, I think all of this you can read lah, and then you can try and error to use in your assignment letter. Because I think if I read this all now, it will be the same lah. It will not be, you all will not remember it also. So just refer to this table if you want to use jump letter. So whatever that is applicable to your assignment, because there are a lot here. Okay, unsigned and signed, and then there are jump based on equality, there are jump based on the status flag. So there are 4 tables that you need to refer later lah if you want to use jump. Okay, so this is the example of application of using comparison and jump. Okay, so for example, you need to jump to a label if unsigned EAX is greater than EBX. First, we compare the EAX and EBX. After that, we need to jump to larger. Larger is another label. If you remember, label is the number that is the word that it's like a go-to lah, yang go-to tu. Okay, we will see later in this. This one. Okay, so this is like whatever label you want to put, as long as you put this one, this two. I forgot all the name of this one. Who remember the name of this?
Column.
Column, semicolon kah? Column lah, column. Okay. So whatever, this is what we call as label. Whatever, it doesn't matter whatever words that you put here, or as long as it is followed by colon, then it can be jump. Whatever instruction can jump to this label as long as you code it lah. Okay, so for example, in this one is actually a label. So just imagine that there's a label followed with the colon previously lah. Okay, so for this task, you need to check, or you need to label. You need to jump if the label. If this condition is met, EX is greater than EBX. So dia punya cara is, first you compare EX with the value in the EBX, and then you jump. If you remember, this JA is jump if the above is true. Okay. I screenshot that already actually. JA is jump if above, which is your left operand is greater than right operand. Okay, so you can jump to larger level if this is fulfilled. Okay, so for this one, we use JG. Okay, so unsigned and signed, they are different. Although this thing using, this instruction has the same purpose, but because each of this instruction will produce different operation in the processor, because to process unsigned with the signed and the signed number will be different in the processor. That's why we need to use different instruction, although it has the same purpose. Okay, so use JG for assign to compare left operand with the right operand. Okay, so for unsigned, we use JBE if we want to compare either the left operand is less than or equal to the value from the right operand. So JBE used for unsigned, JLE used for signed number. It has the same purpose lah, to compare or to make sure that left operand is less than or equal to the value from the right operand. And then this is the little bit expand lah. Bukan detail. The extension of the previous. So if we want to compare unsigned AX to BX and copy the larger of the two into a variable named large. Okay, so in this instruction, we don't know which is the larger, which is the smaller lah. We don't know. Either AX is larger or BX is larger. So we need to first compare. We need first move the value of bx into a large variable. Okay, so just remember lah, just imagine that we already declared this large in our data section. Okay, so first we move the value in the bx because we don't know the value in the bx, right? So we move it to the large and then we compare ax with the value in the bx. Compare AX with the BX. After that, JNA. JNA is jump if not above. Okay, so jump to the next if the above is not if not above. Okay, jump to the next if this is not fulfilled, meaning if AX is not if we want to compare, meaning this one is larger, then this is smaller. Okay, so we jump to next if AX is smaller than BX, and then we move the AX into large.
Nothing.
Tada? Yes, Kelvin?
What is a jump? What is jump?
Jump?
There's nothing. There's no condition. Jump and which one's larger?
First, because we don't know who is the larger, kan? because we don't know. So first we just assume that bx is large lah. So we put it in the large variable. After that, we compare ax with bx. Wait, the compare. We go back to the compare either. If we want the destination is larger than the source, we need, this is for sign pula. Okay, sorry ya. For unsigned, if destination is larger than source, we need to check either zero flag or carry flag is zero. Carry flag or and zero flag is zero. JNA. We should actually check the value of zero flag and carry flag here. But in this example, they didn't show the zero flag and carry flag because we are not using the real number here because we don't know the number. But I think this is the general step of how we can compare two variable or two number that we don't know the value, and then we want to know who is larger. So I think just follow this instruction lah. Okay, so later maybe if you are coding this, maybe you can just use all the instruction and then the instruction and the structure of this, meaning who is first, who is second. Okay, meaning if you want to compare two number, then you need to move something in the some variable first, and then you compare between the two, and then you JNA, or you can use whatever relevant jump instruction here, and then you move the I mean you move which is the register or the value that is large lah to the variable large. Okay, so this is actually just some guideline lah on how to compare. Okay, so for the sign number, we can use this guideline. Use JNL. JNL is jump if not less. Jump if not less. Okay, so if we didn't code this, of course we don't really understand this. Unless we do our own code, then we apply. Okay, so that is just the guideline lah. You can follow it, or you can do it by yourself using another jump instruction. Okay, so another application is we jump to level 1 if the memory word pointed by ESI equals to 0. JE is jump if equal. Okay, so we want to compare either the value in this memory is the same with 0 or not. So we will jump to the LI level if this is the same. Jump if equal, meaning jump if these two equal. Okay, so jump to level L2 if the double word in the memory pointed to EDI is even. Okay, so we use JZ. JZ is JZ. Jump is 0 if I'm not mistaken. JZ. Jump if 0. Okay. Jump if 0. Okay, jump if 0. Meaning if this is even, these two number is even, jump if 0. Jump if 0. Okay, so if we compare these two, double word in the memory pointed by the EDI is even, meaning if it is even, if your 0 flag equal to 1, so the if here is the 0 flag of this one is is 1, and then we compare it with 1 here, meaning both side or both operand is 1 lah, then jump to L2. Okay, so this is the example of application, the fifth example. For example, there are tasks jump to level 1 if bits 0, 1, and 3 in AL are all set. Or all set meaning all are 1. So 0, bit 1, 0, 1, 3, 0, 1, 3, 0, 1, 3. Okay, so that is bit 0, 1, 3. Okay, so the solution, if there are a question like this, jump to level L1 if bits 0, 1, 3 are all set. So set, remember, if I'm mistaken, use OR. Okay, no, this one we didn't use OR because we are testing or using compare and jump. Okay, so the solution here is, the suggested solution is clear all bits except the bits in 0, 1, and 3 position. Then compare the result with this binary, because we know that this is the binary that is meant by this instruction. Kan? Okay, so the way is we can clear, it said that clear all bits except 1, 0, 1, and 3, and then if you remember just now, if clear, we use N. If we want to set, we use OR. So the solution here, clear all bits except this one. So we use N. We N whatever value inside the AL. We don't know what is the value inside AL, but whatever it is, we just want that the bit inside this position are set, meaning 1. So whatever it is, whatever value in AL, we don't want to know. We just want to make it the bit 0, 1, and 3 is like this, so we can use N. So this instruction is clear at unwanted bits, and then we need to compare this to this, because after we end it, meaning in the AL, it become the value, it become this value, and then we compare the value in the AL after it become this one, and then we compare it with this one, because this is the value that we expected. Okay, so that's why we compare it. Okay, so JE is jump if the 0 bit is 1. JE, I keep forgetting. JE, jump if equal. Jump if equal. Okay, so if the value in AL equal to value in the this second operand, then jump to L1 level. Okay, so after that we proceed to the condition loop instruction. So this is loop. Okay, so I don't know if I want to show you this video first. Loop Z, loop. It means this one is actually okay. Loop E meaning loop if equal, meaning you loop to the destination. Loop you need to loop if the previous instruction is equal, and then loop Z meaning loop if zero. Loop if the previous instruction resulting in zero. Okay, so the logic is we store the current counter to the ECX register for the 32-bit processor, and then if the ECX is still larger than zero and the zero flag equal to 1, we need to jump to the destination. Destination is any level, any level. Okay, so this is useful when scanning an array for the first element that doesn't match a given value. Okay, so in 32 bits, ECX is the loop counter register. So in 16-bit, CX is the counter, and in the 64-bit mode, RCX is the counter. But RCX is never used in this course because we are only up until 32-bit. Okay, so for loop NZ, so it is actually the same with the previous, it's just that N is stand for not, meaning it's opposite with the previous. Okay, so loop NZ meaning loop if the previous instruction resulting in not zero. I mean anything, any value as long as it is not zero. Okay, so for the loop not equal, so loop at E, you will need to loop to the any level or destination as long if the previous instruction resulting in not equal value between two operands. Okay, so the logic is the same like previous. ECX is the counter, it holding the current number of counter, and then after that, if the ECX is larger than zero and the zero flag equal to zero, we need to jump to the destination or to any level. Okay, so it is useful when scanning an array for the first element that match a given value. But this note didn't give any example for this. I think maybe it is not, I don't know. Maybe it is not the highlight of this course. That's why it only gives us just some definition. It doesn't have any example. And then we proceed to the conditional structure. Okay, so this is where we will learn about the block structure, which is the if statement, and then the compound expression with n, compound expression with or, while loops, and table-driven selection. Okay, so here we can see the exact example of how we can translate whatever in our high-level language. For example, here is C++ or Java to assembly language. So you can use this. You can use this structure or this code to do if else. Okay, so if else, if operation or variable one similar with operation 2, then x equal to 1, else x equal to 2. So how to do this? First, we move or we assign the op1 to EX, and then we compare EX with OP2. And then after that, we can move to L1, which is X equal to 2, if it is not the same. Okay, so remember, if you compare here, JNE is meaning you go to this like else you go to li is x equal to 2, x equal to 2. Okay, so JNE is more or similar like else. Okay, so this one is for this first block lah, first block. So JNE is like else. You go to li if it is not the same, meaning of1 is not the same with of2. So JNE is like else. So just use this example or this structure if we want to use if else. So another example of if else is this one. But actually, it already gives the answer here. Okay, so if we want to do this, we can just follow this structure in assembly language. Okay, so actually there are multiple solutions to any of this. You can use, it is not necessarily like this. You can use whatever instruction that we have learned previously. So you are free to experiment with all of that instruction. But this is the solution that we can, one of the alternatives lah, of how we can convert this to assembly language. And then, okay, so this is another example. You all can use this structure or this example to do your assignment letter. So if you have some condition like this, you can use its suggestion here to use JLE, to use the charm. Okay, so you can see here. After that, okay, compound expression with N. So this is the details about how we can use compound expression with N instruction. So because in the previous notes kan, there are only one condition here. But if we have any other condition like this one, there are N here. There are more than one condition. Then we can use the example in the next slide lah. Okay, so when implementing a logical AND operator, when we want to implementing this AND operator, consider that the higher level language use short circuit evaluation. Okay, so for example, in this following, if the first expression is false, then the second expression will be skipped. Okay, so it only will check the previous condition first. If this is not fulfilled, then this one will be skipped. It will not be checked by the assembler. Okay, so we see the example. Okay, so if we have, let's say we have these two conditions, and then this condition must be fulfilled because it's N. Okay, so this is one possible implementation. First, we need to check the first expression. We need to compare AL and BL. Okay, so you can just jump to LI if it is better. You, I mean, just use this structure. Just use this structure to do if else that have more than one condition. Okay, so you can follow this structure later. Okay, so another implementation is using this one, and then this have lesser code than the previous one. Okay, so you can choose. Whichever structure or code that you understand the most now. Okay, uh, this code use 29 lesser code by reversing the first relational operator. So we allow the program to fall through to the second expression. Okay, so you just follow this lah, okay? If you want the lesser code. And then if you want to code something like this, there are also two conditions here. Then you can follow this one. Okay. Actually, this one you can test it in the Visual Studio. You can just copy paste this in your Visual Studio code or assembly file, and then you test it one by one. And then compound expression with OR. Okay, so when implementing the logical OR operator, consider the HLL. This is also the same one. The HLL is high level language. It also uses short circuit evaluation. Meaning short circuit, it will not evaluate the second condition if the first condition are not met. Okay, so in this example, the first expression, if the first expression is true, the second expression is skipped. Because or right, it doesn't matter, it doesn't need to for these two conditions both are true. As long as the first condition are met, then you can the next instruction will be processed. Because or meaning either one is true, then the next code will be processed or will be run. But if the first condition are wrong, then baru it will proceed to the next condition lah. But if the first condition is met already, then it will not run or read the second condition. Okay, so it will directly run or process the next instruction. Okay, so this is the example of how we can code the OR with the compound expression. So you all can just follow this code. Okay, so while loops. Now we proceed to the while loops. Previously, it is if else, right? If else and the compound and with the and and or. But now we while loops. Okay, so while loop is really an if statement followed by the body of the loop, followed by an unconditional jump to the top of the loop. Okay, so if you don't understand this, just see this example. While we are doing this, we want to loop this. I'm sure you know what does it mean kan in the high level language. Then we just you can follow this. This is the possible implementation. Okay, so for this one, for this example of this while loop, you can use this one. Okay, after that, actually kan, there are a shortcut for this, for all of what we have learned in the loop structure and then the conditional structure. So we will know, actually, there are if-else. We can use if-else level later, which is in the next slide. Okay. So for the conditional control flow directive, that's why I want we finish this in one lecture so that it will not be dragged until the next lecture. Can I borrow your time? Maybe at most 15 minutes.
Okay.
Okay.
Okay. So only about 9 slides lagi. Okay, conditional flow directive. So actually there are if-else statement in assembly language. So we don't need to really use the previous example, okay, because they are if-else statement in assembly language. Okay, so when we are creating if statement, we will use the runtime expression. We will use all of these. Okay, so this is runtime expression. The runtime expression is .f, .else, .else if, .elif. Okay, so this runtime expression can be used to evaluate runtime expression and create block structure if statement. Okay, so if we want to do this, if else this, we can use it like this. I mean, sorry. This is the example lah. This is you want to compare only one condition, and then this is how you compare two condition. Okay, so this is like, if it is like this, it is just like the high level language lah kan? The structure or the block are the same with the high level language. Kan? Agree kan? If else.
So this one can be used in
Yes.
the assembly.
Yes.
No.
Okay, so we don't need to pecah-pecah kepala to feel, to think, using comparison lah, jump lah. Okay, so because in the assembler they are already they already designed this lah, if, else, and if. So we can use it like this. Okay, because MASM generate the hidden code for us. It is consisting of the code level, comparison, and conditional jump instruction. Whatever we have learned previously that it is very hard to remember, our assembler already did the code behind all of this. Okay, so the assembler do it for us. Okay, so to use the if-else here, we can also implement all of these relational and logical operator. So we can use this equal to, or not equal, or larger than or equal, smaller than or equal. This is not same or false. Meaning whatever, I mean it is complement lah. Whatever is the expression, it is not it. Meaning it written true when the expression is false. Okay, so all of this, I think it is the same with the logical operator that we have learned in high level language lah. This n is equal to n. This two block macam L ni is or, and then the expression 1 and expression 2. We can use this carry followed with the question mark to return true if the carry flag is set. Okay, so we can use overflow followed by this question mark to return true if a flow flag is set up. Okay, so the same with parity, sign and zero. Okay, so this is actually what is behind the code for the if else. What the assembly did behind the scene is this one. To compare this one, what the assembly did behind the scene is this one. Okay, so MASM, this is our assembler, MASM. MASM automatically generate an unsigned jump, which is JBE, because value 1 is unsigned. Value 1 is unsigned number. Okay, so our assembler already know which instruction to be used, either because they will read the variable that you use. If it is signed, then it will use another instruction. But for now it is unsigned, so it uses JBE. Okay, so because this one is signed number, so it uses JLE. Okay, so this is what happened behind the scene. Okay, for this instruction. Okay, so this is also what happened for this instruction. So we actually don't really, if you want to understand this, yes, go on, it's better. But now we already have this one. So I think you can use this in your assignment later. Okay, so there are also dot repeat directive. And then it is used together with until. So this is used, for example, the questions is you want to loop and then you want to print 1 until 10. Okay? So you can use the repeat directive, which is you want to repeat this instruction until you need to put until at the end of the instruction that you want to end up. Okay, so write the DEC meaning write decimal number. So CRLF meaning you want to print or you want to go to the next line. Okay, so in your console letter there will be 1 until 10 number. So we can use, instead of loop, we can use repeat and until. So there are also a while directive. So this can also be used, instead of using loop, we can use while. So while you will be used together with NW to mark the end of the loop. Okay, so this time we want to display 1 until 10 and then we can use while. Okay, so summary. We have already learned about AND or XOR and NOT and test, and then we also already learned about the comparison. And then we already learned about jumps and loop. Okay, so there are various jumps instruction. So the jumps instruction are based on the equality, and also it also jump based on flag value. It is also, there are also a jump instruction that is only specific for signed integer and unsigned integer. And then we already learned the general information about this loop, because we have no example for this loop in this slide. And then we already learned the flowchart. The flowchart is the logic diagrammatic tool, or the previous this one, the repeat, all of the shortcut that um, already configured by, already developed by the assembler developer lah, for to make the assembler language programmer easier lah, to make us easier. So it's like how we code in high level language. Okay, so I hope this, after we learn all of this, you can apply it in your assignment lah. Okay, so try to apply it in your assignment using all of this. Okay, and try to answer tutorial 6, because the tutorial 6 is the tutorial for lecture 10. Okay?
Okay.
Okay, so you try to do that first. If you don't know, then later I will give the answer, the suggested answer lah for this practical. Sorry, for this tutorial. Okay, tomorrow we will do practical lah. Practical for this lesson. Okay, so sorry for borrowing your time. Okay, so if you don't have any question, then we can end now lah.
Okay, Miss.
Okay, bye.
Okay, Miss. Thank you.
Okay, bye.